Deep in the hyper-arid Tadrad-Akakis Massif of Libya lies a geological anomaly defying basic geomorphology. This region sits on a tectonically stable craton. For millions of years, this landscape has been shaped almost exclusively by wind and sand erosion. When researchers look for organic remains here, they expect typical taphonomic baselines, like isolated subfossil skeletons of fish preserved in ancient dried lake beds. But a 1982 core drilling mission, followed by a high-density airborne LiDAR survey, quantified a structure far exceeding the expected scale of the region. This topographical map of a massive, sinuous ridge fits a perfect sine wave formula. The data shows a 99.2% statistical correlation to biological serpent locomotion. Its structural dimensions are immense. Length, 22.4 kilometers. Average width, 18.6 meters. Height, 12.3 meters. The footprint so closely resembles a primordial serpent, it prompted a forensic investigation. Does the internal anatomy prove an organic origin or complex geological mimicry? The immediate uniformitarian assumption was that this elongated ridge was simply a yardang, a standard rock formation carved over time by wind and differential weathering. Simulations show true yardangs form parallel to dominant wind vectors, eroding into asymmetric teardrop geometries. But the Saharan Titan actively cuts across seasonal trade winds. Harmattan winds strike the ridge's lateral curves at extreme angles, ranging from 45 to 90 degrees. Despite facing these chaotic, cross-cutting wind vectors, the structure retains strict bilateral symmetry along its entire 22.4-kilometer length. This contradicts standard aerodynamic erosion principles. Furthermore, if this were just a weathered sedimentary gradient, the edges should be diffuse. Instead, the boundary between the ambient porous sandstone and the hyperdense core forms a microspatially sharp interface of less than 2 millimeters. By 2025, international petrological consortiums concluded that standard wind deflation and sand erosion models fail to explain the ridge by a massive margin. Surface processes physically cannot carve a symmetrical shape across dominant winds. The cause must be generated from deep within the rock's internal root structure. To find that cause, the investigation moved underground. During a 1982 core drilling mission into the primary ridge, the bit easily penetrated the soft, porous outer sandstone before violently grinding against a hyperdense crystalline inner core. The recovered samples proved this was no standard sandstone remnant. The chemical and density differentials were far too extreme. This split-screen chart illustrates the stark contrast. Ridge internal core, 2.82 grams per centimeter cubed, composed of 94.3% SiO2, 3.8% CaCO3, and 1.2% Fe2O3. Ambient host rock exhibits 18.4% porosity. Ridge core exhibits less than 1.1% porosity due to total void-filling quartz metasomatism. This extreme density gives the core a compressive strength of 285 megapascals, compared to the 42 megapascals measured in adjacent yardang formations. These metrics indicate an aggressive process called quartz metasomatism, occurring when an original matrix undergoes rapid, total replacement by supersaturated silica solutions. The ridge's interior is not a passive sediment bed. It is a localized zone of active chemical replacement, mimicking the petrification found in fossilized bone. To map the internal geometry of this quartz matrix, researchers initiated forensic micro-CT scan audits in 2017 and 2023. Inside the solid sandstone, they discovered preserved cellular-scale polygonal boundaries, measuring exactly 12 to 35 micrometers in diameter. Look closely at this micro-CT cross-section. You are seeing interconnected, three-dimensional tubular microchannel networks that perfectly resemble biological vascular or fluid transport architecture. These branching channels are continuously lined with iron oxide, or hematite. There is zero geological sedimentary analog for this kind of structure. The mystery deepened in 2021 when stable isotope mass spectrometry isolated trace organic carbon residues trapped inside these very tubules. The analysis yielded negative carbon-13 values, ranging from negative 18 to negative 24 per mil. This isotopic signature indicates that an organic precursor material was present. At the microscopic level, the presence of carbon-13 isotopes trapped inside vascular-like fluid channels suggests organic life served as the foundational template for the 22-kilometer structure. The core morphology suggests a biological origin, but at a scale millions of times smaller than the ridge itself. This is a microbial phenomenon. The engine behind the anomaly is a process called microbially induced calcium carbonate precipitation, or MICP. Specific ureolytic soil bacteria, primarily Bacillus species, are the biological agents responsible for this localized biomineralization. Here's the biochemical trigger. Urease-producing cells hydrolyze urea, generating ammonium and carbonic acid. This pH spike forces rapid precipitation of calcium carbonate rings around the cells. Phase 2 is metasomatic replacement, where high-pressure supersaturated monosilicic acid floods the environment. The bioavailable calcium ions and organic biofilms act as low-energy nucleation sites, triggering the rapid precipitation of amorphous silica directly onto the bacterial cell walls. This process occurs so rapidly it locks in the three-dimensional cellular geometry of the colony before any mechanical collapse can occur. These microscopic vascular networks are the preserved fluid transport architectures of billions of bacterial colonies that once colonized an ancient riverbed. Applying this microbial diagenesis model to the macrogeography explains the 22.4-kilometer anomaly through a process known as fluvial channel inversion. The anomaly began as a sinuous subterranean river channel. The channel bed became heavily colonized by bacteria, gradually cementing into a solid mass through hydrogeologically focused MICP and siltcrete precipitation. Over millennia, aeolian deflation stripped away the surrounding uncemented sandstone. The hyperdense microbial riverbed was left standing above the desert floor as a positive relief ridge. The vertebrae-like segments are the result of post-mineralization tectonic cooling, which induced regular perpendicular stress fractures along the longitudinal axis of the rock. To differentiate this structure from a biological macrofossil, we can look at the internal architecture of a real fossil. A true biological remnant, like this fish, displays distinct concentric osteon patterns and biogenic skeletal frameworks. The cross-sections of the Saharan Titan show none of those features. Instead, we see horizontal cross-stratification and syntaxial quartz overgrowths cutting directly through the regional sedimentary stratigraphy. The Saharan Titan is an abiotic geomechanical shape, the result of stress fracturing acting upon a microbially cemented paleochannel. Fluvial channel inversion explains the shape of the ridge, but it does not account for the thermodynamics found inside the 1982 core samples. A 2026 forensic geochronological reevaluation exposed highly localized thermal stress vectors buried deep inside the ridge. The reevaluation found the presence of high-pressure polymorphs of silica, tridymite, and cristobalite within localized core clusters indicates the petrification process occurred under elevated temperature greater than 300 degrees Celsius and pressure conditions inconsistent with surface aeolian processes. The Tadrad-Akakis rests on the Pan-African Mobile Belt, a highly stable Neoproterozoic crystalline craton that lacks the recent tectonic or volcanic plumbing required to generate localized 300-degree surface fluids. Standard fluvial and aeolian surface processes operate at ambient temperatures, whereas the presence of tridymite requires a high-energy mechanism current models struggle to place in a stable craton. The mechanism capable of injecting a high-pressure thermal solidification flush into a hyper-arid, stable craton remains completely unidentified. Cut to black.